So today, what I want to talk about is something that we probably all know something about: code. Title of the talk was Interaction Protocols, but really what we're talking about code. Now, most people may be thinking code that we type in, but I'm going to actually go back a bit more to the origins of code and where does some of this come from, and some of our how code affects so much of our life. So I'm going to go through a bit of the history of protocols and then show how they can apply in a programming context, which is kind of interesting. And we all have personal codes. We've got things that we like. I really like coffee. I find I need to have good coffee as part of my life. It's one of my own personal codes. You go to many hotels, and one of the things I get to do is I see a lot of the world with traveling, and some places have terrible coffee. I think they must actually send people on courses to make it particularly bad. United States of America is a really good example of this. They seem to make some of the worst possible coffee in the world. So we have to cope. As developers, we get creative. We do some interesting things. Like, how about this as a way of making coffee when you're stuck in a hotel and you're getting rubbish coffee? There's usually an iron in a hotel room. You bring your trainer so you can go running to keep fit for a bit and bring your own coffee pot. We can do these sorts of crazy little things. But as developers, we do these fun things, the crazy things, and we kind of get proud of them, but is it really scalable? Is it what allows us to do bigger, more significant, interesting things? Just a little while ago, we happened to have this was going around the news where we took the first picture of a black hole. Now, this is not a hack. You can't do this sort of thing as a hack. This is building upon years and years of scientific research and teams all working together. Like, this photograph took 5 petabytes of data. 5 petabytes. We couldn't move that amount of data around the internet. Why it was delayed in getting announced to people was moving some of the data, and one of the reasons that it was difficult was we used 8 telescopes around the world, including one on Antarctica. And to get the data back from Antarctica, we had to ship the hard drives, and planes can only land at certain times of the year because we have codes and protocols. It's not a good idea to land a plane in Antarctica in the winter. It's kind of bad. So these sort of interesting things, these things come up in our lives in all sorts of interesting ways. I'm going to try and argue over the course of this talk that protocols, I think, are one of the most significant discoveries in human history, probably up there with language and other things, and how they impact our lives and the things that we do. And we'll bring it forward into how can we code and write software to actually do better with this. So, what is a protocol? We've probably all heard this. We're terrible in this industry of giving names to things and using it inappropriately. For example, I get really annoyed when I see things like Google protocol buffers. They're not a protocol. They're a codec. They allow us to encode messages that become part of a protocol, but it's a different sort of thing. So we need to be kind of careful. So what is the history of protocols? Well, if you're looking at it from a sort of normal, everyday perspective, we're talking about a code. So as I mentioned to begin with, it prescribes a strict set of rules that we have to adhere to. So we hear about etiquette, but actually more important to me that we often miss is precedence. So the order in which things happen is really important to do these things and do them kind of well. From a software perspective, we often will hear this sort of term where we're looking at protocol, where we're talking about the conventions that governing the treatment and the formatting of data in electronic communications. That's normally what we're thinking about. When we're talking about treatment, we're talking about the behavior, we're talking about the etiquette and the precedence. Again, this is important. We often just think about the formatting, and when we just think about formatting, we're missing some of the really important parts of this and what we need to consider. Now, let's go way back, and then we'll sort of work our way forward. So a lot of where we think of protocols comes from evolutionary biology. So people like Charles Darwin, when he was studying a lot of history and evolution, he discovered certain common things that were happening. So one of the examples of this is that we have behaviors as humans, and these behaviors transcend all languages, all cultures, and they're innate in people, even people who have not learned to speak. There's been unfortunate examples of some people in the world who've been brought up and never even been taught language. But they have some things that they know, and that's things like understanding facial expressions. These things are totally sort of ubiquitous around the world. Like, we understand joy, we understand disgust, we understand sort of happiness, various things. We can express these, we can even see it in some other animals as well. Now, the disgust is actually really important, particularly for how we survive and how we go forward as a species. I'll come back to this one very, very shortly. But so we have this history, like even in our biology, hardwired into our DNA to how we behave. We refine this as we've gone forward as people. We have manners and we have etiquette sort of going on. So manners is kind of what we think every day, and etiquette is kind of more formalized. The word is a French word. It means little card or a little note, and it's basically giving instructions about what we should do. This was first formally really introduced by Louis XIV at the Palace of Versailles, where you put little cards out like, walk on the right, stay off the grass. All of these things that we kind of maybe have heard. This is the origin of some of this. It tells us what to do, how to behave. It becomes really important. Like, manners is quite a formally studied subject. It's broken down into 3 layers. First layer is our basic hygiene manners. So we need this, otherwise we will propagate disease. So if we think about things, we will behave in a certain way, and this helps us stop propagating disease around a community. This is good for us surviving and sort of going forward. And this is where things like the disgust comes in. We express disgust, and this helps us avoid disease. So we'll stop spreading disease. But if we see someone who's obviously diseased, we will stay away from them. We'll show disgust. If we see food that's got sort of excrement in it or something bad, we'll walk away and go, ugh, that's kind of disgusting. This is a useful thing. It helps us survive. We should also be applying this in our technology world. Like, I've been programming now for 35 years, and I've seen some pretty disgusting code over time. I've done a lot of JavaScript, I confess, and some of it was downright disgusting, and we should have isolated that and not let it spread. Unfortunately, we let some of the really disgusting technology spread, and we're now living with endemic diseases now as a result. So we're not even following our hardwired human principles around some of this. So we should think. So sometimes whenever you see something and you get that feeling inside of disgust, trust some of your DNA programming. It's telling you avoid certain things. Don't propagate it. Don't let it continue. Like whenever we started configuring servers with XML, I felt really bad. But why do we keep doing that? If you had seen someone with smallpox, you would have stayed away from them. That's our kind of DNA. It's kind of wired to that. So kind of think about that. But it also applies to things like isolation. This is why things like encapsulation is really important. It sort of wires into how we work, how we scale. Next layer up from that is what are known as courtesy manners. And these are important for as we start to scale. So we've covered basic survival, but then once we're surviving, how do we scale? Well, we show courtesy to show that us as an individual is not more important than the group. The group is actually more important than any of us. Like our tribe, our community, whatever should succeed, even if we don't. That's part of biology, is how we should be. So it's things like, let someone else go first. Let someone else eat first. Think about people. Show respect for elders. These are kind of basic inbuilt things that are really important to us. So we got to think about this, and we should show it in the courtesy. Like, who's going to come and read your code later? It's a nice courtesy to them to not leave a mess. We kind of like, we do this sort of thing. It's like you don't leave a mess in your kitchen. You don't leave a mess in your bathroom for people to come to follow. Similar things considered in the code. We come up to the highest layer, and that is the norms. And this is where we normalize what we do. And by normalizing what we do, we make things more efficient. We build trust. Because if we see people behaving in a way that we expect them to behave, they're kind of showing they're part of our community. It's all part of the bonding process, and that gives us more trust. It makes us more efficient in our interactions. We don't need to isolate people so much if we trust how they're interacting. Someone comes into your community and they're behaving odd. What are they doing? They're doing something unpleasant, nasty. You will isolate them. You'll take away the trust. These sorts of things, so we've got to think about it. So again, it's like when we build systems, we interact with other parts of systems, we show conventions, we show trust, we can start to scale some of this stuff. It gets really interesting. Some of the most advanced stuff out there is done by the military. So the military's done so much research on protocols to how we do things well, in particular when it comes to war, because war is a kind of really bad thing for humanity. We want to be very careful of it. And so most militaries around the world have got rules of engagement. If anybody spent time in the military, they'll become aware that the rules of engagement are often explained to you. One way of looking at it is considering what is acceptable. What is acceptable when you go to wars? Because you really don't want to do this sort of lighthearted. You've got to be much more careful about it. And by thinking about what's acceptable, we can constrain what's going on. I've seen some really good talks by people from the military field. I happened to be at a conference, and one of the other speakers was a guy called General Mike Jackson, quite a famous British general, and he describes things in a very interesting way. He does not consider war as something where you go to crush or you destroy your enemy. He says the whole purpose of war is to change someone's mind. It's because you've had a disagreement. If you don't consider that, you're actually missing the point. And it's kind of interesting. So think about, like, if we're having arguments or discussions, the point is not to beat someone in an argument. It shouldn't be. That's actually failing. The point is to try and change someone's mind or have your own mind changed because you're running on poor information. This is the sort of stuff that should be wired into us at a lower level. Also, we'll talk about you should set things up with good conditions to succeed. Like, most of our views of the military, we think this is like to bomb stuff, blow stuff up, but actually behind it, some of it's quite fundamental in how they think about stuff. So we have to think about what is success going to look like, what is good going to be as an outcome, and usually that is minimizing the harm that will be done. Like even back to in olden days, two armies wouldn't battle typically if they could avoid it. You'd typically pick your two champions from each side and resolve it, be the champions. It's an easier way, a lot less loss of life. We've codified this at an international level with two bodies of law. And you hear with justa bellum, justa bello. One is the right to go to war, and the other one is how to do war rightly. And these are legal positions that we take. It's the big difference between if you follow this body of law, you're considered a soldier. If you don't follow this body of law, you're considered a murderer. And that's how things stand sort of globally. So we've got interesting history in some of this. So I'm kind of fascinated by protocols in general, so I've sort of read around the subject a lot and sort of found all of these interesting sort of things that are out there. But what you probably really care about is computers. We'll see how some of this starts to come together, particularly concurrent and distributed systems. We have to use these all of the time. We're getting ever more concurrent with loads and loads of CPU cores. These are also concurrent across machines, so it's distributed on top of that. And what we fundamentally want to look at is how should systems interact? What is the rules by which they should engage with each other, and what way they interact starts to govern their behavior? Now, one of the best bodies of work we have out there is the IETF, the Internet Engineering Task Force. This specifies protocols for how our systems should interact. It's one of the reasons why the internet is so successful, because it's a set of rules that everyone follows. And as it works, it scales, it works really nicely. And they produce RFCs and other papers that are really useful. Now, what you find is every April, particularly on the 1st of April, we get a new paper, and it's usually one of the funny papers. So since I like coffee, I particularly found this one interesting. There's a hypertext protocol for controlling coffee pots. And it sounds like a joke, but it's actually quite well written and sort of covers some interesting things. I particularly like things like, it's got an error code, 418. Would you return going, sorry, I'm a teapot? And so we can have a bit of fun with this, but it's also quite informative. This is one of my favorite papers from the IETF. And if you've ever done any encoding of integers, you wonder, like, what's this big endian, little endian thing? This paper describes it better than anything, and it's a 1st of April paper. Now, the reason why we talk about big endian and little endian integers is we sort of think, are we sending the big integer first for the first big byte, or the little byte first, and when we send them in order and we go to read them? But the origin of why they're called that is Gulliver's Travels in Lilliput, the book, and there was two tribes in this, and they warred. And the reason they warred was over which end they eat their eggs from first. When you eat your egg, Do you turn it up with the big end first and you smash that and you eat that end? Or do you turn the egg the other way and smash the little end first? So big endian or little endian? So we end up with these kind of silly sorts of things. So this is kind of another fun paper, but describes brilliantly why we have this term of big endian and little endian integers and how we encode stuff. So one that's really worth reading, kind of recommend it. Like other fun examples that we have out there is how do we transmit IP using pigeons, avian carriers. So we can send this sort of stuff, and this is kind of interesting. This got inbuilt collision avoidance because they happen to be pigeons, but it's kind of low bandwidth, high latency, and how it works. This was taken forward. It was updated when quality of service was an important point. We then took it even further forward for IPv6 recently. So there's the kind of fun side of all of this. And so you can get into some of this stuff. You can start reading about how this stuff's done in a fun way and learn things whilst you're kind of doing that. But there's also a lot of serious stuff here too. But so look at, well, how do we document our protocols? Like, we've seen examples there using the IETF, but every day we're not going to produce a full RFC for our code. That seems to be a bit much. What should we be doing? How should we be thinking about some of this? And I find there's this really interesting debate about API versus protocol. And I think the problem exists here is because people now kind of understand what an API is. They don't understand what a protocol is. And so we kind of look at this thing in the sort of wrong way. An API, I think, is only one very small part of the puzzle. It very importantly misses the precedence part. So when we talk about how we're going to interact with the system, saying what things you can call on it, it's got some value, but it's very limited because it says nothing about the precedence. What order should things be called in? Now, here's a simple example. Let's say I want to use a file. I can open a file, I can read a file, I can write a file, or I can close it. I can do other things, but let's keep this nice and simple. So imagine defining your protocol for interacting with a file using a simple regular expression style syntax where I open, then I can follow it with 0 or more reads or writes, followed by a close. I've now specified precedence. This is much better than just giving an API. It tells me what are the order of which I can perform operations. It's not complicated. We could use extended Backus-Naur form. We could use lots of other ways of describing this. I quite like the regular expression style syntax of doing this. It becomes really useful. And then from there, we can go on and we can enumerate each of the operations and what they do. Going through that exercise, when you produce a service and you're saying, how can I interact with that service? Try producing a basic protocol like this, and you'll find that you'll start to realize you don't know enough yet. You maybe need to go to talk to the customers. You need to discover stuff. You'll then do a better job of writing the service. And this isn't complicated. This can be like one page of text is all you've put together. It really helps us with our thinking process and doing this well. And really importantly, as we start doing all of this, especially when we're dealing with concurrent distributed systems, one question should always be in your mind. What could possibly go wrong? We kind of hear this, but do we actually practice it? We so often program for the happy path, but as we start getting into more distributed and more concurrent systems, you have to think about what can go wrong. And particularly, what if messages arrive out of order? What if these operations happen in an order you don't expect? Like, what if somebody calls close before they call open on a file? Is that valid? What should happen? What happens if somebody calls us close and then calls write? How should it behave? But should that be a nice, friendly sort of thing? There's a great paper I recommend you go read. If anybody hasn't read this, please go read it. It's a good analysis of what was causing P1 outages in production, so errors that caused the entire system to stop. And it's a great analysis of what it was and what can be learned from it. Like, I particularly like some of the quotes like 75% of all of the P1 outages could have been tested with a simple unit test, but weren't. Much more important for me was the fact that 25% of all of the errors that caused an outage in production was because of an ignored error condition or an ignored exception. Within those, it was even worse when they analyzed the code. So many cases, there was a to-do inside an exception handler going, we should fix this before we go into production. It wasn't done. And that's just the simple things that we should be doing. It's really important and starts to make quite a difference. So go read this paper. If you walk away from this and you don't think of anything else that I said, that's okay. Please go read this paper. It'll make you think differently about writing tests and making sure your code's complete. It's the protocol for how you interact as you're working day in, day out. You need to consider some of this stuff. Now, let's go for a different example here, something a bit more concrete. So imagine we're working on a distributed system and it's going to be a chat server or it's going to be a whiteboard or something that you've got a lot of shared state with a lot of users connecting to it and you need to see what's going on. Now, I'm going to use a real example that was developed back some time ago and some of the papers that came out of it. And one of the things that was really popular at the time was people starting to consider sort of how do we scale things, how do we make it work? Well, if you start developing a system like that, you got some interesting problems. So all of the users connecting to it, they need to see the data. And they need to make sure they don't lose any data. So what do they do? Do they acknowledge the data that's been sent to them? And then they get more data and it keeps going that way. Well, this has got a scalability problem because if you have to acknowledge all of the data that's sent to you, as the number of users goes up, you don't scale. You've got a problem from any single node. Well, you could federate and fan out, but that's adding another layer of complexity. You can approach it from a different approach, and that's where you could say, well, I'm going to use a NAC-based protocol rather than an ACK-based protocol. So rather than acknowledging everything that you get, is you just assume data is going to get through successfully, and if it doesn't, you send back a negative acknowledgement saying, I didn't get the data, please send it again to me. So the ACK ends up with this implosion of too many ACKs. The NAC seems to be a really good idea. The only problem is NACs and loss tends to be correlated. So for example, if the server is going to send out the data, it goes to send out the data and it fills the buffer that is sending the data out. It's been sized incorrectly, there's a stall on the process, something's going on. You fill the buffer and you overflow the buffer at this stage, so you end up dropping some data. It'll end up being correlated for every single client that's reading that data. So they'll all not get that data because it doesn't propagate out. They'll then all send NACs back. If they all go to send NACs back, you get a NAC implosion because this gets even worse than even the ACK case because they all send NACs back. The data all gets retransmitted again. It had a problem because you're already at the limits of what you're capable of. You're now multiplying the data you've sent by the number of clients all over again, and now you're into this catastrophic congestion collapse scenario, so it doesn't work very well. And in the 1980s, when we were working on the internet, we started getting a lot of congestion collapse and went through into the 1990s, and some people like Von Jacobs and Sally Floyd ended up working out what was going wrong, and they fixed it, and the reason the internet works really well today was because of the work they did on congestion control. Well, on this particular problem, Sally produced this really interesting paper. It was like, how do we deal with this problem? And the way they dealt with the problem is really simple and very elegant. So whenever you don't get the data, so whenever you realize I'm missing some data, you don't send a NAC straight away. What you do is you set a random timer. And this random timer will go off between now and some time in the future. It can be actually a relatively short period of time, and you can calculate the ideal time based upon the round trip time to the server. And then of the various clients, the random timers start to pop at different stages, so they expire. Whenever your timer expires, you check, has this data been resent? If it has been resent, you don't send your NAC. If it hasn't been resent, you send your NAC. And so now what we've done is we've distributed out the possibility of sending the NAC back to the server. The first one that sends it, it'll get to the server, the data will be resent again to everyone. It all works, and all the others don't send the NACs again. It's really simple. Notice there's no central coordinator, there's no central control. It's actually a beautifully elegant algorithm that scales really well. Now, if anybody knows anything about Sally Floyd, you start to realize, hang on, why did this person come up with algorithms that don't require central control and are very scalable and work really well? Now, Sally has a PhD in computer science, but her bachelor's degree is in sociology. She understands the scaling of communities and societies. And so the behavioral patterns are different. And so we can learn a lot from other ways of looking at this. Now, the way these timers were going off is they're on a standard distribution. So you can still get some issues. It's not ideal. You can get multiple timers fire around the same time. It worked fairly well. And then some people took the work further. This paper was produced a little while later. And so rather than using a normal distribution, what we'll do is we'll use an exponential distribution on this and we'll skew it towards the back. But knowing the round trip time and the group size as a rough figure, doesn't have to be precise, we can actually have enough timers will pop early. We'll actually get less knacks, we get a lower latency and works even better. Again, no central control, just applying good math and good protocols. Kind of really elegant stuff. I know this stuff works really well because when we developed Aeron as our messaging system, these are the two primary algorithms we use for scaling out with multicast, and they work beautifully. It works really nice. It's really fast, really low latency, and doesn't require brokers, doesn't require central control. It all works nicely peer-to-peer, based upon the protocols of someone who had studied sociology before they studied computer science. So kind of interesting history and ways of learning about this. So there's a couple of samples. Where should we focus in this area? Because protocols are a pretty big subject. There's lots of things to consider, like how do we layer stuff, how do we version things, what encoding mechanism, addressing, flow and congestion control, I mentioned error handling, the whole sync versus async debate, trust, privacy. There's loads and loads to this. I'm not going to go into everything about protocols. I want to kind of whet your appetite a little bit for it. But let's pick on a few areas and explore them a little bit. So first of all, ask a question. Who here cares about waste? Care a little bit? Well, here's something to consider. If you care about waste, our data centers now are using more energy globally than the airline industry, by quite a bit and rising all of the time. And most of that is our poor, crappy code. I get to measure lots of real world systems and see people's code and see where the time's wasted. And often the bulk of the time is spent parsing text-based codecs. We end up using text to encode stuff. JSON, so XML, people's homegrown codecs, it is really, really inefficient. So one thing is like when you start thinking about protocols, if you want to be even remotely efficient, and not even about being fast or super fast, just caring about waste, start using binary codecs instead. They matter so much more and they work a lot better. Now, to our laptops and our desktops and stuff, now, that matters a bit. To our phones, it matters even more because the amount of battery life you spend wasting parsing text and sending all of this down, like the size of the average web page is terrible. So I'm old. I'm kind of used to computers in the past. My first processor was a ZX80, like really kind of small, kind of tiny, and so we worked my way up from there. Like, I was around whenever sort of Doom was a cool thing and Quake and some of those games. The Quake server is now smaller than the average web page of all the text and JavaScript and all of the CSS we send with all this stuff and images because we just are getting really, really efficient or inefficient in how we deal with this. People will often say to me, when you say this, but it's human readable. I want to do text. I don't like doing binary. Think about it like you do your kids. I want to eat candy. I don't want to eat my vegetables. I don't want to eat salad. Well, sorry, you got to kind of suck this up. It's not human readable. A few people I know can read ASCII. I know virtually no one who can read UTF-8. You happen to have an editor that's good at that. Humans can't read it. We need tooling that gets better at this. And with the tooling, we can do a better job. We can end up doing this in a kind of nicer way. We can draw pretty pictures. I get to play with ASCII art sort of most days when I'm defining messages. And if you're in the IETF, these are sort of normal things we end up doing. What options are there? There's things like SBE, flat buffers, kept in Proto. There's lots of options out there for binary encodings. And they're not a little bit faster. We're not talking 20%, 30%. We're talking 2 to 3 orders of magnitude difference between using a binary codec and using text when you come to processing stuff. So it's just vast amounts of waste. So you start thinking, well, how should our systems interact? First step is please stop using text to talk between machines. And actually, computers don't read text very well. They're much happier with binary. We're making them do text because we can't be bothered having the tools or understanding some of the things that are out there. I'll kind of move on to that. Versioning, another interesting topic. It's worth looking into. Versioning applies at a number of levels. First of all, we want to version our protocols themselves. So within a given exchange, what are the valid interactions we're allowed to have? Is there new messages allowed in this? So my file, I can open, I can close, I can read and write. My new version might support seek. Another version might support truncate. So knowing which version you've got, knowing which are the valid verbs you can use in any given interaction. So it's important to put a version number on your protocols. The messages themselves should be versioned. So if we add new fields, we should be able to add new fields to existing messages, and someone with a newer client can read the additional fields. Someone with an older client don't see the new fields, but they should still be able to interact with the message. So that means that the new fields must be optional. We must design and think that way to do it well. This sort of stuff, people get a reasonable understanding of it. I'm finding the versioning of state to become an incredibly powerful thing. And the more I study this, I'm sort of realizing I wish I had discovered some of this 20 plus years ago, because it is so powerful and this is not so obvious. Like, let's have some examples that are sort of reasonably easy to understand and then sort of a bit more subtle. So one relatively easy thing to understand is if you're into consensus protocols or anything we're dealing with distributed systems, you'll find that most of the modern protocols now put version numbers on all of the messages, particularly for the state. So for example, if I'm going to have an election to find which is the leader of a cluster, when I'm having the votes, I want to know which election I'm voting in. I don't want to be voting in the previous election or some other election and get mixed up. I want to know that my vote is for this election now. So the election needs to have a version. This sort of stuff works really well. It's fundamental. If you don't do this, you'll end up with very brittle systems, because you'll get a message that's appeared from a previous election or out of order, and now you're really confused about it all. But it's much more subtle when you get into things that are concurrent, not just distributed systems. So I've worked a lot on queues, and multi-producer, multi-consumer queues are kind of fascinating. They're very complex. They're reasonably well understood to what the behavior should be, but they're complex by their interactions. And some of the ones I've worked on, where I've been extending some of the work of Leslie Lamport's from the 1970s and through the 1980s, we can do some quite cool things with them, but it starts to get really complex when you try to make them very fast. And I discovered with some of the implementations I worked on, I didn't take care of some edge conditions very well, particularly around the full and empty state. And we get what is known as the ABA problem, where a state can go from what looks like one value to another value and back to the same value. But it's actually importantly two different states. Even though it's got the same value, you can't tell them apart. You end up making the algorithms very complex to make it work. I discovered this website about 10 years ago, the 1024cores.net, and Dmitry Yukov has got a really nice, elegant implementation of an MP-MC queue in that. And what's totally unique about it compared to other things is he versions all of the state. So when you're putting things into the queue and you're removing things out, everything gets a sequence number, which is the version number. And they sit alongside. And so when you get into the wraparound cases of full and empty, you don't have the ABA problem because everything has a sequence number. I remember when I read this algorithm, I was just like, wow, this is obviously correct. It's not overly complex, it's simple. And it sort of relies on state. So the state being versioned is important. I'll show you another example just shortly. We get the whole debate of synchronous versus asynchronous in systems. Which one shall we do? How does it pan out? Well, let's look at what's involved in synchronous communication to another web service. We'll send a request, we get a response. We'll send another request, get a response. Send a request, get a response. That's kind of what we're sort of expecting, and time is expanding over this. So it takes a certain amount of time for those three interactions. If we end up with a higher latency, things are further away, our network's a bit slower, we send requests, get response, requests, responses. Now I can't get through the three requests in the same point in time because latency is becoming an issue here. I need to think about this. And what's happening whenever I'm in this stage? Like, so I go to send the request, I got to wait on the response, my thread needs to be put to sleep. I need to be context switched at that point. Something else gets to run, context switch back later. We end up having a lot of overhead in the operating system to make these sort of things happen. If we're asynchronous, we send a request, We don't wait. We send another request. We send another request. And then the responses start to come back again, asynchronously. This is the world that we're in. We are actually disconnected. We're separated in space and time. We increase the latency. What happens? It doesn't have as big an impact on the time. So being asynchronous is much more efficient. It also models much better what's going on. So what's happening in this case is like I can be sending with non-blocking sends and receiving with non-blocking receives. And if there's nothing to be done, I can do something else. I don't need to ask the operating system to be involved. I don't need to get context switched. I don't need to take that overhead. We can do a lot more, and we can also be a lot more cache-friendly staying on the same CPU core. But again, I get this again, but synchronous is so much easier. It's a bit like but text is so much easier. We're behaving like children with candy. But I like the taste of it. I don't like the other stuff. Even though it's good for us, it's the kind of thing that we should be doing. We need to think again about this. Think about it from a word perspective. Synchronous is a kind of nice word. It means we're coming together at a rendezvous, we're synchronizing. But really what we're talking about is blocking. We're stopping progress, we're halting, we're stalling. It's a different way of thinking about stuff. And you can sort of dress it up with futures and dealing with stuff with fibers and coroutines. It's just masking over. It's like trying to take the strawberries and dip them in chocolate to get people to eat them rather than, so it's sort of trying to give them candy. You've got to get over some of our inbuilt feelings on this. And it's about managing the feedback. It's manage that feedback. It's get over our instincts. So we are so used to, we want instant feedback. So that's a good thing, but also we got to know whenever it's not a good thing. Like candy tastes great. It's very instant feedback, but it's got a really bad long-term consequence. Eating your salad, eating your vegetables is not so nice on instant feedback, but much better in the long run. We got to break some of that basic DNA conditioning that we have. And if you're trying to have this bottle, the easy way to think about it is, well, write your whole system as async and then wrap it with synchronous to make things work for a bit. So this is at least gives you a migration path. Don't just build a synchronous system because you can't go to asynchronous again so much easier. So it becomes an easier way to think about this. Like, we see this all over the place. I have seen the times we've come around to RPC now. About every decade we sort of say, we're going to have another go at RPC, and then we realize it's a really bad idea and we give up on it, and it comes back again. And it keeps coming back over and over again. It's just like each generation forgets what the previous generation discovered of how bad this was. And our current flavors of doing things like RPC with REST and different things over HTTP, which is totally the wrong protocol for interacting with things. It's designed to fetch documents, yet we're using it for other things. And then we're doing that over TCP, which TCP was not designed for this. TCP was designed for long-running connections, not short-lived connections. It ends up hurting quite a bit. So we end up with lower level stacks evolving, trying to cope with the bad things that we're doing above. We're using these underlying abstractions incorrectly. So TCP is getting things like fast open to get around the three-way handshake to begin with. Now, even with later services, we're not using TCP. If you're using a Google service, so if you're using Google Chrome or you're using sort of the Google Docs or anything, and you're talking to their back end, you don't use HTTP over normal TCP. You're using a protocol called QUIC, which is using UDP underneath. So it's trying to retrofit for some of our bad behaviors. Like we've seen this with HTTP 1, we went through Speedy to HTTP 2. We've also realized that there's mistakes in HTTP 2. We didn't think about what can possibly go wrong. By sending everything down the same connection and we have a problem with it, we end up with the issue if we don't get the rest of the page rendering. So now we're having to have redundant connections to make sure we get some page rendering happening. And so now with HTTP 3, we're having to think about that. We've seen it with security, TLS 1, going to TLS 1.2 to 1.3. That's actually a really nice protocol change. Things have got more efficient, cleaner, safer. It's kind of moving in the right way. You can go read the spec on that if you're kind of interested. But here's where things that apply really well is like, so you jump to TLS 1.3, it's a really nice protocol and it's got a faster way of connection. It's got a zero round trip connection. But that has an implication if you don't design everything else right. If you don't realize, that means replay attacks can happen on your system. But if you version all of your messages, and you've seen that version of the message before, it's now idempotent. You're not vulnerable to a replay attack. So building up your protocol, thinking of the different components of it, we can make it much better. We can also batch your system. So this is where we can start to get much more efficient and friendly with our systems. Now think about etiquette here. So imagine we go around to a friend's house, and you're there to have dinner, and your friend says, I need something from the store. Could you go get it from me? So you say, okay, I'm going to go get some milk from the store. You go get the milk. You bring it back to your friend whilst they're making dinner. You sort of would do that sort of thing for your friend. You get back again, and your friend goes, do you know what? You didn't get enough milk. Could you go back and get me another pint of milk? And so you go off and you do it again. You bring it back. You come back again and say your friend says, do you know what? I actually need another pint of milk, and I need a block of cheese. You said, now you're sort of thinking, as a friend, you're not very nice. So some of these instincts start to kick in. But what's kind of happening is we will do these things with our friends. We will do these things with people because we have some inbuilt natural behaviors that we know that sort of thing's wrong. When it comes to a computer, we don't think that way. We just ask it to go to disk again, like, go get me 1 byte. That's fine. Go get me another 1 byte. Rather than give me the whole thing in a go to work on a reasonable sized chunk, thinking about that. Now, computers don't have feelings, but it's kind of interesting that whenever we want to do something really unpleasant as humans, we deliberately dehumanize the people we want to do something unpleasant to. It's instead of getting practiced at being dehumanizing, we need to be more practiced at having more humanity and actually thinking with some empathy and some sympathy for the hardware we're running on, then we can get much more out of it. So again, tapping into our natural ways we're wired. And this starts to matter. As we move into 100 gig and further, we can't use our synchronous blocking calls. Like our operating systems are now at the point where they realize we can't do this. You can't use the normal BSD sockets and try to drive 100 gig or greater Ethernet because the syscall overhead per sending any given packet is too high. The per packet costs are really terrible. We need to think differently. We need to think about batching. We need to think about different ways of working, different APIs, different protocols. And we're starting to see that with some of the APIs that we have. So like Linux, we've got like send end message, receive end message. We've got ways where we can send multiple things across in a batch. We're getting user-based stacks that avoids the system overhead, so things like VMA, open onload. And now with new APIs like DPDK, EFVI, and others that are there, it's a totally different way of interacting. We need to do this. Now, people will say, oh, no, we're going to solve this problem. We're going to take our synchronous calls and we're going to run them in fibers. Sorry, it's not going to work. It misses the basic physics of what's going on. It sort of papers over some short-term problems, but there's fundamentally different ways we need to be thinking. We need to think about the protocols that we interact with these things with. And so think about how do we naturally batch? How do we do sensible things and sort of behave with some sympathy for what's underneath? We can get much more. So let's think about the sort of more unpleasant side to it. So corporates, they want to deceive us. They want us to buy their products often. Now, sometimes our corporates are trying to do the right thing. They're trying to help us, but more often than not, they want our money. And so they want to convince us they're going to take away all of our problems. And if they take away our problems, things get easier for us. They'll sell us silver bullets. Two-phase commit, or XA, is a really good example of this. It's a terrible protocol that's been proven to be incorrect and flawed, yet we keep getting it peddled all of the time. One of my favorite papers describing two-phase commit is this one later by Jim Gray and Leslie Lamport, where they highlight a lot of the issues and what's wrong with two-phase commit and how we should do things better. Like particularly pointing out two-phase commit is not fault tolerant because it uses a single coordinator. It's a single point of failure. We can't be having that. No sociologist would have designed a protocol to look at this. Imagine Sally Floyd looking at that protocol. She would have been showing disgust at just the flaws in the design. It's an arrogant way of thinking, and it's designed to make people think it's a good way of doing stuff, but it's not a good way. You hear it also with guaranteed delivery. Like any messaging system that promises you guaranteed delivery, the snake oil. They're lying to you, trying to trick you into thinking you have responsibilities as a developer that you need to consider. The things can be there to help you. We can make things better, but it doesn't get rid of things. You've got to know about versioning. You've got to know about feedback protocols. You've got to know about recovery protocols to do the right sorts of things. So we've got to think about how we deal with this, and if we do, we can do it much, much better. And think about it. When we're building on all these layers, what are we getting from the layer below? We often will make the mistake, and I'm as guilty of this as anyone, is we know the implementation, so we take advantage of the implementation. But it's not necessarily what the protocol should be offering us. So we get to the stage where we offer correct protocols, we describe them well, people can build on them safely. They know what they get. That allows certain things to be easy changed, easy dealt with, easy to understand the boundary cases, and then we build on that, and we compensate at a higher level, not take the tricks of what's below. It becomes much easier. So let's wrap up. Getting back to our protocol is the most significant thing for humans. I'm going to explore this question. So throw out a different one. Anybody recognize this protocol? Should do. Scientific method, originally back to Francis Bacon, sort of made popular by the likes of Newton and many others. Like, this allows us to achieve really great things, but we've got to follow the protocol. We've got to do the right sorts of things. Like, it sits alongside another great thing is falsifiability. So if you're into science, this is so important. So how does this fit? How does you think? Well, you start thinking about testing. If you're going to release any software, you've got to think that your testing process, CI/CD, is about falsifying should this piece of software ever make it into production. That's what your whole pipeline is trying to do. You're trying to verify that it's correct as much as you can, but you're also trying to falsify should it make it into production. So what does that mean for your protocol of development? Whenever you go to test something, you should write the test and see the test fail first. Because otherwise you don't know the test is actually working. If you write the code, then you write the test, and everything goes green, which is right? What's wrong? It's not science. What have you verified? Other than you've got green. If you write the test, you see the test fails, so you've showed that the current system is falsified against its actual requirements. You then can fix the system, and you can move forward. So it's a great way if somebody ever reports a bug as a process, define the test first. Write the test, see the test fail. Now you've demonstrated what's wrong with the system. Now go fix it afterwards. Simple protocol, simple interaction. We can learn a lot from how we work on this. Also think about when you go on to your next project. When you start your next project, do you install all your favorite tools, all your favorite languages, all the technical rubbish that you want to play with? Or do you think about, what is the thing I'm supposed to do? What is the protocol of interaction of the component that I'm going to build? And will it offer to the users what they require? It starts to be very different in how we think about things if we do that. And kind of just one last thing. Like, if you want a brilliant example of how protocols have fitted into society as a whole, virtually every society on the planet has come up with some variation on the golden rule. Like, you'll see it in religions, you'll see it in non-religious things and stuff, but the basic summary of it is you try to do to others what you would like them to do to you as a way of behaving. I think about that from, if you write code, if you do anything, is you want to make things nice for other people to interact with. Making something unpleasant, making it difficult, it's not so good. And also consider that you, in 6 months' time, is a different person. So your own code, you're going to come back to it. Leave it in the state so that you're thinking about what your interaction is going to be with it at that stage. It makes things a whole lot better. And on that, I'll thank you very much. I think I've got time for a question or two. Any questions? No? Okay, thank you very much then.